maybe you should sit closer to it so you can see.
All right, well, last time we derived a formula for the connection gamma SIL as G SK with a 1/2 times G KI comma L plus G LK comma I minus GIL comma K. And of course this is assuming that our formula for the gammas, which is the regular Levi-Chibita formula, and it is ES dotted into the partial of, say, EL with respect to XI. And so that's our definition of what gamma is. And now we can consider, now that we have a formula for this, we can consider what the covariant derivative of the metric tensor would be. And it would be GIL semicolon K. So far we've considered covariant derivatives with respect to vectors. Now we're doing a covariant derivative of something that has two indices, like the metric tensor. And let me give you the answer, and then I'll give you a derivation. So this is GIL comma K minus gamma M IK GML minus gamma N KL GIN. Okay, and now that I think about it, this original derivation I should have done for a general covariant tensor and then specified what happens to the metric tensor, which has the property of being symmetric in our version. In fact, most versions of general relativity is symmetric. So let me see if I can do it on the fly for this more general case. So let's, what will I call this thing? Let's call it T. So I want to do T comma K. So this would be, I wrote G because that's what's in my notes. So doing this on the fly may be a little tricky. TIL, EI, and I need to do something, maybe I'll just write them like this, EI, EL. So this is sort of like a tensor product of two vectors. Okay. But I'm going to leave out the X with the circle. All right. And it's this whole thing, comma K. Okay. So this is going to be TIL comma K times EI-EL. And then it's going to be TIL EI comma K EL. And then it's going to be TIL EI-EL comma K. So that's the whole thing. And so the point is, this is a second-rank covariant tensor, and then these are two vectors that are contravariant, and the whole thing then is an invariant quantity, and we're invariant of the coordinate transformation. And so we're then taking its derivative. And now, as we did with the covariant derivative of a vector, we're going to take the inner product of this with the vectors that are dual to EI and EL. And so when we do that, we're going to let us say, do En dotted into T comma K. And so this is going to be the En is going to pull that down to Mn comma K, because Em is orthogonal to Ei and En is orthogonal to El, unless, it's delta, it's a Kronecker delta. And then the next term is going to be plus TIL, and then we're going to have, let us say, Em dotted into Ei comma K, and then this En is going to make this, this is going to be delta Ln. And then the next term is going to be TIL, and then that's going to be delta Im, and then En dotted into EL comma K. Well, these things here are not exactly the gammas, but remember we derived the formula for them by differentiating the Kronecker delta formula of E upper I dotted E lower J. And so what we found was something like this. Em dotted into Ei comma K is minus gamma I mk. Okay. And so now what do we have? What we have then is we can call this TMN semicolon K. So TMN semicolon K is this, or the whole right-hand side of that. And so that's equal to the first term, which is TMN comma K. And then the next term is delta Ln, so it's TIN. TIN, and then this thing, Em dot Ei comma K, it's minus a gamma. So I'll put this as parentheses, minus gamma I mk. And then the next one is TIK, TML. And now we've got this thing, which is going to be minus gamma upper L NK. And it's NK. Okay. So now if we write it out simply, what we have is TMN semicolon K. The covariant derivative then is defined as TMN comma K, and then two minus signs. And the first one is minus TIN gamma I mk, and then minus TML gamma L NK. Okay, so this is the formula for a general for the covariant derivative of a general second rank tensor. All right, now let's specialize this to the case of the metric tensor. And so for the metric tensor, it's just GMN semicolon K. So it's called GMN comma K. and then minus, if I write it slightly different, gamma I mk first, and then g I n minus gamma L nk GML. So in the particular case of a metric, it's this. All right, the next step is to use this formula. That is to say, our formula for the gammas, our formula for the connection. And we have to use it twice. We have to substitute it here and there. And so what we find, and and for some reason in my notes, I changed from MK to IL, and I think maybe there are so many indices, I'll just follow my notes rather than try to do it on the fly. So what we have then is GIL semicolon K equals. By the way, the answer is going to be 0, just to make a long story short. It's going to be GIL comma K, so that's this term. And then substituting for this, we're going to have minus a half GMS GIS comma K plus GSK comma I minus GIK comma S, and then minus a half G NS GLS comma K plus GSK comma L minus GLK comma S, and then GIN. All right, so this term was actually that term, and that term was this term. I don't know why I transposed them in the book, but anyway, it is. Okay, now, huge cancellations. First, what do we have? This, of course, is the inverse of G with lower indices, and yeah, I left something out. There's a GML here. Yeah, I left that out. This is GML. Okay. Now we have an obvious cancellation. First of all, remember our metric tensor is symmetric in its lower or equivalently upper indices. So this with that gives us delta SL. And this with this gives us delta SI. So let me do that on the fly here. Trying to find an eraser that more or less works. So what we'll get here is delta SL. And here we're going to get delta SI. And so we get rid of these two guys. Okay, but now, since S is L, we can do surgery on this and just replace S by L. So I'm going to have an S, I'm going to have an L here. I'm going to have an L here. I'm going to have an L here. And over here, I'm going to have an I. So S goes to I here. Okay, so now we should see some cancellations. Well, first of all, this guy cancels this one. And this one cancels that one. And then if you keep track of the fact that this guy is symmetric, well, They don't cancel, but the two together cancel this. And so altogether we have the result, the GIL semicolon K 0. And notice that, in particular, if our metric tensor hadn't been symmetric, this last cancellation wouldn't have occurred. I think all the others would have occurred, but on the other hand, we used our formula for the connection in terms of the metric tensor, and that's specific to the Levi-Civita tensor. So anyway, but in normal general relativity, this is the result, GIKs. The covariant derivative of the metric tensor vanishes. All right. Okay, the next topic is the divergence of a contravariant vector. And it turns out that if you just start thinking about this, you'd think, well, this is going to be so complicated. In fact, it turns out to be very simple. It's a remarkable cancellations. So I guess just to use all the black space, I'll start here. So what we're talking about is the divergence of some vector, and this is vi semicolon I. And we know from our formulas that that's just vi comma I plus gamma I k vk. Okay, now the point is that this is quite simple. There's a nice formula for this. And in fact, we can look at it, namely we already have our formula over here for what gamma actually is. We use that formula over here. And so we get that gamma iik is equal to a half GIM times GIM comma k plus GKM comma I minus GIK comma M. Okay, so that's our formula. And in fact, these last two terms cancel. And that's not immediately obvious, so let me actually show it to you. So we have GIM, GKM, comma I. And using the symmetry of the metric tensor, we get this. And now, M and I, this is a remarkable case where we have two contractions. So M and I are dummy indices. So they don't care what we call them. And we can call IM and MI. If we do that, we get GIM, GK, I, comma, M. So I've just interchanged M and I. And then I'm using again the symmetry of the metric tensor. So this is GIM, GIK, comma, M. So this and that are the two terms that occur here multiplied by GIM with opposite signs, so they cancel. So we have this remarkable simplification, namely that that the contracted connection is a half GIM, comma K. And okay, so that's great, but in fact there's an even nicer expression for this, which comes about from matrix algebra and determinants. And I don't know how you feel about determinants, I'm happy with determinants of 2 by 2 matrices. Anything higher and I start to get seasick. But anyway, we can know. Let me just say what. So first of all, I'm going to use this notation. G underscore is going to be the metric, let us say GMN. So this is the metric tensor with lower indices, and I'm going to use G upper for the matrix that is, let us say, G upper MN, whose entries are G upper MN. So this is a 4 by 4 matrix whose MN entry is GMN. So I'm just using the underbars and upper bars to indicate which it is. Okay, so let's consider the determinant of the matrix that is the covariant metric tensor. Then the determinant of any matrix is the sum over I or L of GIL times the cofactor CIL. And let me remind you what the cofactor is. CIL is minus 1 to the I plus L times the determinant of G bar with row I struck out and column L struck out. So I don't know how to write that symbolically, but it's that stuff you learned in high school, and then you learned again as a freshman in college. And if you're like me, then you got it. And but that's what it is. Okay, and now let's then look at this and let's imagine for a moment that we're considering the case where G might not be symmetric. So we're considering GIL and GLI as two different variables, which is fine. So I'm going to take the partial derivative of determinant of G covariant with respect to GIL, and that, of course, is CIL. It's the cofactor. Okay, so that's one nice result. Another nice result is what we learned when we studied determinants and cofactors and so forth, is that the inverse matrix, or equivalently G upper bar, or the inverse metric, or matrix, what is that? Well, it's the transpose of the cofactor, so it's CLI, divided by the determinant of the matrix. So the basic matrix is G covariant. You take its cofactor matrix, transpose it, divide by the determinant of G bar, and that gives you the matrix that is the inverse of G covariant. Okay. All right. And now we see this is GLI, CLI, but remember, CIL is the partial of the determinant of G under with respect to GIL. So if we do LI, this board is getting crowded, but maybe I have enough space to do this. Namely, what I can say is here, the GIL, that's this, is going to be 1 over the determinant of G covariant times CLI but CLI is the partial derivative of the determinant of G underscore with respect to G L I. Okay, that's Li. So this is our formula for GIL, which is the inverse matrix, or the contravariant metric. All right. Now I think we're going to have to switch over here. So we've got our formula here. GIL is equal to 1 over determinant of G partial, let's see, what did I do? Partial determinant of G bar with respect to GLI. Okay, great. Now, let's just use the chain rule. Determinant of G bar, comma K. So we're taking the derivative of that. Well, that'll be partial of the determinant of G bar with respect to GIL times GIL comma K. And again, we're not using here the symmetry of the metric. And so this is equal to GIL comma K, but now partial G bar, partial GIL is G upper, and I should switch it to IL, so it's LI. Let me get that straight now. I've gone nuts here. It's this term, partial that is times determinant of G underscore. Okay. So that's our expression for this thing. Now we go back to the case of the symmetry of the metric tensor. And our formula for the contracted connection, which is this. And so, writing that down again, what we have is gamma IIK is a half GIM comma K. Okay, now let me try to get this straight. Well, all right, here we have this structure, GIM comma K, and we call this GIL comma K. So all of that is what? It's just the partial derivative of the metric tensor's determinant divided by the determinant and then a 1/2. So it's 1/2 determinant of G underscore comma K divided by the determinant of G underscore. All right, so that's basically our formula, namely that the contracted connection has this simple form in terms of the determinant of the metric tensor. Okay, we're now going to transform that twice. You might ask why, and this is kind of conventional. We could just stay with this. This is a perfectly correct formula, but what people do is they first of all set G equal to the absolute value of the determinant of the metric tensor with, again, lower indices. And you might say, why absolute value? Well, because this thing is -1, 1, 1, 1. So generically, the determinant of the metric tensor is negative. So we want an absolute value because we like things to be positive. And so if we do that, we can just flip in the absolute value signs like this. whoops, like that. And now we can say, well, what is this? This is just G comma K. No, it isn't G comma K. That's, yes, it is G comma K. So this is G comma K over 2G. And the next thing is, well, we don't like this 1/2, and so we use square root of G comma K over square root of G. If you do the arithmetic, you see this is the same thing. You might say, well, why do we have the square root? Well, one reason is that you get rid of 2. Another reason is that in all sorts of formulas, we want to integrate over space. So we integrate over dx0 d cubed x, say. That's space-time. That's flat space-time. If we want a space-time thing that, a space-time volume element that makes sense in GR, we multiply by the square root of G, and that gives us a volume element that's invariant under general coordinate transformations. Because this is 4 contravariant indices, this is 2 covariant indices, but it's a determinant, so it's actually 8 covariant indices, but it's a square root, so it's really 4 covariant indices. All right, so that is basically that. Now, you see this funny thing here, square root of G over square root of G comma K over square root of G. You've seen that remember when I told you what Maxwell's equations look like in general relativity? They're almost the same as the original Civil War era Maxwell equations. The difference is that the inhomogeneous equation gets a square root of G in it. So the ordinary Maxwell equation, you said square root of G equal to 1, you got the ordinary Maxwell equation. This is the generally covariant Maxwell equation. And so you see the difference is really, really super minor. And where it comes from is that it comes from this formula, namely that there's a contracted connection that occurs in there. I could describe what this actually is. There's some stuff with the hard star that makes this kind of cute, but I think that following this hard star stuff is more trouble than it's worth. Anyway, it's in the book if you want to read it. You don't have to. All right. Let's see. Maybe turn the camera just a tad. Okay, so now what I want to talk about is the covariant Laplacian, and because the covariant Laplacian is, well, if you have a scalar, so suppose f is a scalar field, and f comma I, its derivative is a covariant vector. The contravariant vector is f upper comma I, which is GIK f comma k, say. Okay. So what is the covariant divergence of this quantity? In other words, GIK f comma k semicolon I. Well, we've learned what such a thing is, namely, gosh, did I write the formula down? I think I just worked out this, well, this is terrible. I didn't bother to write down the final result. I just derived the gamma. Yeah, this is a bit of a pity. All right, well, let me do this in two steps. Let's just consider an arbitrary, let's consider the arbitrary vector, contravariant vector first of all, and then, so let's just have del dot v. Okay, so this was vi semicolon I, and that's then vi comma I plus, and it's gamma iik vk. And so this is equal to vi comma I, the ordinary divergence, plus, and now let me just get this straight, this vi sub k is this thing, which is that thing. So this is plus square root of g comma k over square root of g times vk. So the covariant divergence of a contravariant vector is the ordinary divergence plus this funny term here, square root of g, the square root of g comma k over square root of g times v upper k. So in particular, if we apply that now to this vector, which is f comma I, then we have f comma I semicolon I would be f comma I plus square root of g comma k over square root of g times this thing, whoops, not v. All right, hold on, I need to get an eraser. F comma k. So that would be the general structure there. And okay, on the other hand, this f upper comma k, upper comma I, all right, let me just, all right, well, you've got this, this index repeated here, we could just as well make it I. And now what we can say is that this thing is square root of g f comma I over square root of g. So when this comma I hits the f, the square root of g's cancel, we get this term. When the I hits the g, we get that term and we have this. And another way of thinking about this is that this is square root of g upper I k, f comma k, and then all that comma I over square root of g. So that's another way of thinking about it. All right, so these are all different equivalent ways of describing things. And let me just put a note to myself in here. Oh, there it is. Okay.
next topic is so this is the covariant Laplacian. And by the way, the Laplacian in 3 dimensions, one sometimes writes it this way. This is di squared summed over I. In 4 dimensions, one often writes it this way, namely d0 squared minus Laplacian. Anyway, so this is in special relativity. In general relativity, it's this sort of thing. All right, the next topic is the principle of stationary action. And I'm going to skip the early part of it because the early part of it is something that you've seen many times. And I'm going to skip then to the special relativity version of it. And so let's write down the action for a particle in particle of charge Q, which of course I wrote G by mistake. Okay, so this is an action for a particle of mass m and charge q in an electromagnetic field, and we're talking in terms of special relativity as opposed to general relativity. And we can rewrite this as minus m. I wonder if this is actually a help. Now that I think about it, I think I'm actually making things more difficult than necessary. Yeah. So let's change the path and. All right, look, I'll follow the notes, but there may be a simpler way of doing it. Anyway, this detour is the square root of minus eta I k dxi dxk. So that's the first term. This is the detour in special relativity, so I've got eta here. And then the next term is plus q, an integral ai of x. And now to put in this detour, what we want to do is have an integral dai detour, and then AI dxi detour times detour. So we want everything with a detour in it. And again, detour is going to be this expression, square root minus eta ik dxi dxk. And this had better be an L or something. And this is an upper L. Okay. All right, so this is the expression in special relativity. And now the key thing is to look at what the variation of detour is. And so this is the variation of minus eta ik dxi dxk. And so this is 1/2, this to the minus 1/2, the derivative inside, or the change inside. But because of the symmetry here inside, the ik symmetry, we can just forget about the 1/2 and just dicker with either dxi or dxk. And so this is then minus eta ik dxi, the change in dxk, and then what's down here is simply dTor. On the other hand, dxi dTor is ui. And so this is minus eta ik ui, and then the change in dxk is d, the change in xk. So this is g change xk. So that's the expression there. And now the rest of this is, we have basically dTor here, and so we're going to vary that, but we also have al dxl there. And yeah, in fact, maybe I didn't even need to fool with this, now that I think about it. All right, anyway, let's just look at what this is. The change in ai dxi is the change in ai dxi plus ai, the change in dxi. And the change in ai is ai comma k, the change in xk, dxi plus ai d variation xi. Okay, so these are the things that we have to put together. And so when we go to the front, there are an awful lot of indices here, and I'm sorry, but I don't know really how to avoid all these indices. So let me clean off the board here. I guess we have to wait for this to dry, so I might as well erase this one too. Although it's so late in the hour that I don't even have time to write on this board. Are there any questions? Okay, so where are we? Putting things together, we have the change in S is an integral, and we're really going from one proper time point to another. And this change looks like this. M uk d change in xk dTor plus q ai comma k change in xk dxi dTor. Well, that's just ui plus q ai d over the change in xi dTor, and all that dTor. Okay. And what we do now on this term is we integrate by parts. And so we expose just a variation of xk. Over here we have a variation of xk, we don't need to do anything. Here we once again integrate by parts, and when we integrate by parts, we have a d dTor of ai, that's partial ai partial xk times uk. And so what this is tau 1, tau 2 minus m duk d tau plus q ai comma k minus ak comma I guess I changed indices here. Yeah, I made this a k. dxi d tau, well that is just ui. And then we have dxk d tau. Okay, so this thing in the square brackets has to vanish, and we get as our equation of motion 0 equals minus m duk d tau plus q ai comma k minus ak comma I ui. And this is the Maxwell tensor, and m duk d tau is pk, and if we raise the index k, lower the index I, then what we get is, or maybe we'd be better off leaving them the way they are. So let us just say dpk d tau is equal to q f ki ui. And the way I wrote it in the book was I raised the indices k and raised this I and lowered that I, but it's the same. All right, I think maybe we can stop here, and next time I'll do the particle and the gravitational field. In fact, there are sort of two ways of doing it. One way is the way I did in the book. Well, I did in the book both ways. The second way is to use the principle of equivalence. And there you just say the particle in the equivalent inertial frame is just moving along at a constant velocity, and but the coordinates in the gravitational field are then related by just a general coordinate transformation, and then you get a structure that looks like you get the equivalent gammas. All right, well, let me give you another candy, even though you didn't ask any questions. All right, I guess we can stop now.